Okay, in this PowerPoint, we're going to go over the renewable energy sources. That includes solar energy, wind energy, wave energy, and the other one, hydroelectric. Okay, as a quick review, don't forget that power is equal to work over time, or in other words, work is how much your energy changes, so change in energy per unit time. We're going to use that a lot in this PowerPoint. Solar energy. There are two types of ways we use solar energy. We can use what's called a heating panel, which we're going to talk about now, or you can use what's called a solar voltaic cell. We're going to talk first about a solar heating panel, and what you do with a solar heating panel is energy comes in, okay, and you have a bunch of tubes that are filled with water or some kind of liquid snaking around. These tubes preferably are colored black so that they will be able to absorb the sunlight. Okay, and then it absorbs the sunlight, gets that water nice and hot. So sunlight comes in, the water absorbs it and gets nice and hot. So it gains, in other words, kinetic energy, which is moving particles, right? So it gets nice and hot, but not all the energy is absorbed, so you lose some. And then what happens is that energy can either, one, go inside the house and then you just use it for hot water. Or if you can get it hot enough, which you can, if you can get it hot enough to turn into steam and be moving really fast, that hot water or steam can move a turbine, so it gives it kinetic energy to the turbine, which you're going to lose some energy again in the process because not all that energy goes into moving the turbine. And then, of course, you can generate electricity from that. This is how a solar heating panel works. Keep in mind, though, it can work in two ways. One, you just get hot water and that's it. Or two, you're continuing the process and you're getting electricity out of it. The second way to get solar energy is by using a solar voltaic cell. A solar voltaic cell is a special device that is made of two bits of special silicone material. You take a silicone, what we call an N-type silicone material, and you sandwich it with a P-type silicone material. And when you do, it creates this junction in between. Now this junction is pretty critical because what happens is when sunlight comes down and hits one side, the P side, it will take these electrons and it will cause them to jump from this side up to the N side, and then these electrons want to come back, but the junction only allows the flow of electrons across one direction. So it excites these electrons, they're free, they move over here, and then they want to go back because this was their home. There's now a hole here where they used to be, and they want to go back there, but they can't because it can only go one way. So what you do is you provide a way for them to go, a path that you want them to go, so some wires from one side to the other side, and now they can go, instead of through the junction, they can go all the way around and go through whatever device you want them to do in the process, so through your light bulb or whatever you're trying to run. And in this way, you can create electrical energy. However, it's important to know that these solar voltaic cells have really crappy efficiency. They only have an efficiency at best of about 30%. So it usually takes a lot of area in order to get enough power to run these things. Okay, so some pros and cons of solar power, right? First of all, solar energy is free. You don't have to pay for the sun. It's inexhaustible. The sun will pretty much always be there. It's clean. It doesn't produce carbon or other greenhouse gases. Some major cons is that it only works during the day, right? You have to have the sun out for it to work. Also, it is affected by cloudy weather. Now, it still will work in indirect sunlight. So, for example, in Seattle, you can still use a solar voltaic cell. However, its production just goes way down. Okay, and it also has a very low power output. That's because of its poor efficiency. It also requires, therefore, a large amount of area to even make them successful. So if you're using the solar voltaic cells, it takes a large amount of area so you can get enough voltage to actually run whatever you need. If you have, instead of solar voltaic cells, if you have the solar heating panels, it still takes a lot of area so that the pipes can snake around and you can warm up that energy. Okay, or you can warm up the water in the pipes. You need a lot of area so you can collect all that sunlight. So it takes up a lot of area, and that's kind of a pain in the butt. Also, the initial cost of both are pretty high, especially the solar voltaic cells, because you're making this special kind of material in order to make it, and it's kind of expensive. However, it is getting cheaper, which is good. So let's say hypothetically we have a single square meter of a solar voltaic cell. That's actually quite a bit, a large square meter of solar voltaic cell. And let's say that 1 square meter only creates, at best, 400 watts of electrical energy. And that is on a sunny day near the equator. That's how much it might create, a whole square meter. So if we want to do something like create enough electricity to, say, run, I don't know, our water heater, typical water heater uses about 4,400 watts. That means that I need one giant square meter of solar voltaic cells is not going to cut it. That means I'm going to need more, right? So how can we get enough energy to actually heat our water heater? Okay, we would just need a lot more solar voltaic cells. I would need 11 of them, right, to get to 4,400. This is power per unit area, right? This has to do with power per unit area because we're taking up for each square meter, right? We get so much area, or we get so much power. So we say we need a larger area to produce a larger amount of power. So this is known as intensity, power per unit area, which is also found in your yellow packet. Which now I just answered this. Your intensity, power per unit area, is found in your yellow packet. It's the next equation. This is the equation we actually use not only in global climate change, but we use it to figure out your solar energy. So one thing you need to know about intensity is that it depends on both where you are and the season that you're on. So if you're high up here, high in the earth, you're going to have a different intensity than you're right here near the equator. This is because as the sunlight comes in, right, it comes in and this beam of sunlight comes on, and when it hits the earth, right, this area or this beam of light will take up only this amount of area. A beam of light coming in from over here, though, when it hits the earth, will actually take up a larger amount of area. So even though it's the same chunk of energy, this energy is spread over a larger area and therefore is actually less intense. So if you have solar voltaic cells and you're up here in Washington, it's not going to be as effective as if you were down in Ecuador. Okay, so different areas might be more effective at using solar voltaic cells or solar heating than other areas. So region matters. Also, season matters, right? Because of the tilt of the earth, when at different seasons, right? So the sun might be shining over here, and at this time, would be winter for the northern hemisphere, right? Because it's hitting mostly the southern side, and so it might be more intense on the southern side than it is on the northern side. But then later on in the year, when the sun's over on this side, it's hitting more on the north, and so it's going to be more intense on the north side than it is on the southern side. So intensity varies depending on where you are on the earth and what season it is. So it will not always be dependably effective. It could be less one time or in other places, depending on, the season and the region. So let's practice a solar energy problem. Let's say sunlight that is coming down it has an intensity of about 700 watts per square meter, which is reasonable near the equator. Okay, so this energy comes in, and let's say the solar panel, we'll say it's a solar heating panel. Let's say the solar panel has only about a 70% efficiency in order to actually absorb that energy. Okay, and then in the process of transferring that energy into the water and sending it into the house, it only has about a 50% efficiency in transferring that energy into the actual house itself. So if the house uses a maximum of, let's say, 4,080 watts or 4.08 kilowatts during its peak usage, what should the area we have take up, or what should the area we need of solar panels in order to provide the house with all of its energy usage, all of its energy needs during its peak time? We want to draw a Sankey diagram to help with this, and then we'll actually try and solve this problem. So here's the problem again. Let's draw our Sankey diagram, right? So we know energy is coming in from the sun. We know it's hitting our solar panels, and it is trying to absorb that energy, but remember, it's being lost. Only 70% is absorbed, some is lost. Then once it's captured, right, only 50%, it says, only 50% actually makes it into the house, this energy. So again, it's lost again. And then what we want to know is how much area, right, we need. So the area is going to affect how much of this incident solar energy we can actually absorb. We know how much we want out. We want 4.08 kilowatts of energy. That's how much we want to get out. So Well, let's take a look. Let's label some stuff. We know efficiency is power in over power out. So we know that we want to get out totally, we want to get out 4.08 kilowatts, right? So that's what we want to get out in the end. But the efficiency, there's actually two efficiencies here. There's an efficiency here where we lose some energy and an efficiency here where we also lost some energy. So before we can find out how much energy we need total, right, to absorb from the very beginning, we've got to figure out how much energy was captured. So out is this amount, in will be this amount, the amount going in this process. We know the efficiency from here to here was 50%, right? So we say, okay, using this equation, we say 50% efficiency, plug in our numbers, rearrange, and we get 8.16 kilowatts. So that is the amount of energy captured, right? Now this amount of energy came from this energy over here, which it lost energy in this process, and it lost by 70%. So we can use efficiency again, right? This time 70%, and this time the stuff coming out in this process is the 8.16. So we plug that into the out, and we're going to solve for the amount going in during this process, and we get 11.66 kilowatts. Now, what do we do with this energy? This is the amount of energy that we know that it is absorbing, right? So this will determine how much surface area we need. If the energy or the power per unit area, yeah, so in other words, the intensity is 700, the question is how much area do we need to take up in order to get 11,600 watts? So what we're going to do is we're going to use our equation for intensity. Intensity equals power over area. We're solving for area. Intensity is going to be this amount over here, and the power that we need is this amount over here. So we plug it in, plug in our numbers, rearrange, and we solve, and we get an area of 16.7 square meters. So for this house, we are using a massive amount of surface area just to run the energy for this house.